Let's look at some more properties of the determinant of a matrix. First of all, if A has a row or column of zeros, then its determinant is 0. That's easy to see just by thinking about the property which we emphasized about the determinant of a matrix A. It's the sum over every permutation of Sn of the sign of that permutation times a product, A1, S of 1, A2, S of 2, up to An, S of n. You will remember that we made the observation that every summand in that sum contains a term from row 1 and a term from row 2 and so on, a term from every row in the matrix. So if there's a row consisting of all zeros, then every single summand in the sum defining the determinant contains a factor of 0. So every single summand is 0. So the whole sum is 0 and the determinant is 0. Next up, if a matrix A has 2 equal rows, then its determinant is 0. That follows very easily from the row swap property. The row swap property says that if you swap 2 rows of a matrix, then the new matrix has determinant minus the determinant of the old matrix. But if we swap the 2 equal rows, then we get the same matrix. So the row swap property would tell us that the determinant of A is equal to minus the determinant of A. Finally, if A has 2 equal columns, then its determinant is 0. Well, you can't quite get this from the things we've proved so far. What you need to do if you want to prove this is to prove a column swap property exactly like the one we proved for rows. So it's really no more difficult. But if you do this, then of course you can use the same argument as part 2 to prove that if A has 2 equal columns, then its determinant is equal to 0. Another technique will be to prove that the determinant of the transpose of a matrix is equal to the determinant of the matrix. Then, since the transpose swaps rows and columns, part 3 will follow from part 2. That's the approach taken in the online notes where you can find proper proofs of the column properties. Let's prove a slightly simpler result now about the determinant of the identity matrix. That's always equal to 1. And it's actually very easy to prove this using the summation definition of the determinant. If we use delta ij to represent the ij entry of the identity, then delta ij is 1 if I equals j and 0 otherwise. That means in the sum defining the determinant, the only term which could possibly be non-zero is the term corresponding to a permutation S, such that S of 1 equals 1, S of 2 equals 2, and S of n equals n. Otherwise there would be a factor of 0, so the summand in the sum defining the determinant would contribute nothing. So what happens when S of 1 equals 1 and S of 2 equals 2 and so on? Well, then you've got the sign of the identity, which is 1 times delta 1, 1, delta 2, 2 up to delta nn. So that's just a product of 1s, and so the answer is 1. Finally, let's work out how doing row operations, actually not quite finally, but let's work out how doing row operations affects the determinant of a matrix. We can now say precisely how a row operation affects a determinant. Remember, there are 3 different types of row operations, so we need 3 different parts in our theorem. First of all, if you do a row swap, then you change the sign of the determinant by -1. We already know this, we proved it. It's exactly the row swap property. Secondly, if you add a multiple of row I to row j, so L times row I to row j, then the determinant of R of A is equal to the determinant of A. Well, this time it follows directly from the row linearity property. The row linear property says that the determinant of R of A is equal to the determinant of A plus the determinant of B, where B has row I twice. It has it in rows I and row j. But the determinant of B is equal to 0 because it's got 2 equal rows. So we just get the determinant of A again. In part 3, take the row operation which multiplies row I by L. We'll then think about what happens in the sum defining the determinant of a matrix. So the determinant of R of A would be the sum over all S in Sn of sine of S times A1 S of 1 up to An S of n. Well, now think about this sum which would define the determinant of R of A. It looks exactly the same as the sum defining the determinant of A, except that there's a factor of L coming from the Lth term in that product in every summand. So every summand in the determinant of R of A is the corresponding summand of the determinant of A, only multiplied by L. So when you factor that L out, you get the claimed result. So we're done. We've proved these three properties which tell us precisely how a row operation affects the determinant of a matrix. A very useful corollary to that is that if R is a row operation, well then R may affect the determinant. It may change the determinant of a matrix when you do that row operation, but you never change a matrix with the determinant 0 into a matrix whose determinant is non-zero. And you never change a matrix whose determinant into non-zero, who was non-zero, into a matrix whose determinant was 0. In other words, if R is a row operation, then det A is equal to 0 if and only if det R of A is equal to 0. That's obvious from the previous slide because we've seen that row operations either don't change the determinant, or they multiply it by -1, or they multiply it by a non-zero scalar. Remember, row operations which multiply rows by scalars are only allowed to multiply by non-zero scalars. That is the definition of row operation. So in any case, none of the effects on the determinant possible can change it from 0 into non-zero number, or from a non-zero number into 0. Next, one of the results we're going to prove about determinants is that in general the determinant of A times B is equal to the determinant of A times the determinant of B. This next corollary is a stepping stone towards that result. It says that if R is a row operation, then the determinant of R of I times A is equal to the determinant of R of I times the determinant of A. So this is like that multiplicative property. In fact, it's a special case of that multiplicative property of determinants. And the special case is when one of the matrices, the matrix on the left, is an elementary matrix. Now again, this is really easy to prove because it reads straight off from the last theorem. There was absolutely no new ideas whatsoever. So let's just do one of the three cases according to the row operation which swaps row I and row J. Well then, from the previous theorem, the determinant of R of I is minus the determinant of I, which is -1. So that identifies one of the characters in this claimed equality. It identifies R of I as -1. On the other hand, the determinant of R of I times A, well, you know left multiplying by the elementary matrix corresponding to R is the same as doing R, so this is equal to the determinant of A, of R of A. But from the previous theorem, that's minus the determinant of A. So on the left, we've just established that's minus det of A. And on the right, we've got -1 times the determinant of A. Those things are equal, so the proof follows. The other two different types of row operations can be done exactly the same way.